Hello and welcome to this video about specialty polymer solution for power electronics in electric vehicles. I'm Nicolas Batailley, Marketing Manager, and I will host the discussion today.
Hi, I'm Victoria Lee. I lead our electrification efforts in our Application Development Lab, and today I'll be providing the technical explanations for our solutions for power electronics.
The first question you may ask yourself is, what is the function of an inverter? Basically, on an electric vehicle, you do have a battery, which operates in a DC voltage, or direct current, and you do have an electric motor, e-motor, which operates in AC mode, alternative current. The job of the inverter is to organize the flow of electricity between the battery and the electric motor.
Like we said, the battery delivers a DC voltage and current that's either on or off. But most e-motors in electric vehicles operate on an AC voltage, which is a sine wave. The AC sine wave required by the e-motor can be simulated by switching the DC voltage on and off for different lengths of time, providing pulses of voltage to the e-motor. Changing the pulses to simulate that AC sine wave is called pulse width modulation, and this is key to providing constant torque but improved power of the e-motor. The switching speed here is really important. The faster you can switch these voltages on and off, the more closely you can simulate an AC sine wave and the more efficient your system becomes.
Let's dive and learn more about the benefits of using specialty polymers for the components inside the inverter.
First, we have the capacitor. This smooths out the DC current coming from the battery and also protects the battery against negative ripple currents that propagate back from the e-motor. Then we have the bus bars. These are usually stiff metal conductors that are insulated with a plastic, and they deliver electricity from one point to another. Then we have the power module. Inside are the semiconductor chips that switch the DC voltage on and off to simulate that AC sine wave. And finally, we have the housing, which contains and protects all the components inside.
Let's start with the power module. The power module is really the key component, the component of the inverter, since it is the part which transforms the DC voltage into AC voltage. First generation of electric vehicles were based on 400-volt architectures. But with the need of fast charging, we see the development of 800-volt architecture, and we need to switch power module from IGBT technology to silicon carbide technology.
Like we said, the faster switching speeds result in benefits like lower losses, higher efficiency, and allow you to miniaturize your inverter. However, those benefits also result in higher temperatures and higher electrical stresses in that smaller space. So the challenge here is to deliver material solutions to our customers that enable this shift to the silicon carbide inverter technology.
Let's talk about the technical requirement for this application. First, we need a material which is flame retardant V0. Secondly, we need to have a material which is heat stabilized, meaning which resists to high temperature from 110 to 150 degrees C. We need to have a material which is halogen-free to limit or avoid any risk of electrocorrosion. Obviously, we need a low water uptake to guarantee a high dimensional stability. And finally, we need a material with a high CTI.
CTI stands for Comparative Tracking Index, and it indicates the resistance of a material to conduct electricity across its surface. We have a prototype here where I can illustrate how this works. The higher the CTI, the closer these two conductors can be placed together without risking arcing across the surface. The lower the CTI, the farther apart they need to be placed. So CTI is a critical material property that power electronics designers use to design their power modules. A high CTI allows them to miniaturize these components.
We do have two materials to answer this requirement. The first one is Amodel Supreme PPA, and the second one is Ryton PPS. Amodel Supreme PPA is a material we introduced on the market 2 years ago, and which offers the highest glass transition temperature, so the TG, available today in the PPA world, meaning we are talking about 165 degrees C. This high TG allows to Amodel Supreme to retain its 600-volt CTI over time at temperature which can go up to 150 degrees C. In addition, Amodel Supreme PPA offers one of the best performances in terms of thermal shock resistance. Obviously, we are able to also offer Amodel PPA with flame retardant package. The second material we can offer for this application is Ryton PPS. Ryton PPS is inherently flame retardant V0. In addition, since there is no ignificant inside the resin, there is no risk of electrocorrosion. Right-hand PPS offer a water uptake lower than 0.2%, which guarantee a high level of dimensional stability. Finally, right-hand PPS is virtually resistant to all chemical aggressions, meaning that's the perfect material for bus bar or AC connectors which are in contact with different fluids. And the last information is that both Amodel Supreme PPA and right-hand PPS resin are produced with 100% renewable electricity. Now, let's talk about the bus bar. The bus bar is a key component inside the inverter. It's critical since it's linked different systems in order to conduct the electric power. What are the requirements for the bus bar? First, we need to flame retardant visual to avoid any risk of flame for safety. Second, we need to be allergen-free to avoid any risk of corrosion. We need to be resistant to high temperature, knowing that a bus bar may experiment temperature up to 180 degrees C. We need to have a low water uptake to guarantee high dimensional stability. We also need to have a high CTI, like for the bus bar. But we also need high chemical resistance when the bus bar is in contact with a different fluid, typically the ATF, which cools down the e-motor. And finally, we need to resist to thermal shock cycling.
Resistance to cracking during thermal shock is essential here. We mentioned before that the faster switching speeds of silicon carbide inverter technology increase the temperature in your system. But when the car's not operating, the ambient conditions can get down to -40 degrees C. So the insulation on a bus bar needs to survive cycling between these two extreme temperatures. But these two materials, metal and plastic, expand and contract to different extents during heating and cooling, exacerbating the stresses that are present at the interface and throughout the bulk of the material, and that leads to cracking. Bus bar designs are all different depending on the system. So we've designed our own internal prototype to be able to screen our materials for their performance during thermal shock cycling. And we can perform that testing in-house, cycling between temperatures as low as -70 degrees Celsius and as high as 200 degrees Celsius. We combine this thermal shock testing with electrical testing, mechanical testing, and testing for the adhesion between the metal and the polymer to get a full, complete view of the value of our materials in this application. And we're developing our fundamental understanding of the thermal shock performance by using virtual engineering simulations.
Here again, we do have two materials to answer to this requirement. The first one is Amodel PPS Supreme, and the second one is right-hand PPS. Amodel PPS Supreme offers the highest TG you can find in the PPA world with 165 degrees C. This material to retain its property, CTI property, 600 volt over time and at temperature up to 150 degrees C. In addition, this material is also available with flame retardant package. The second material is right-hand PPS. Right-hand PPS is inherently flame retardant, it's allergen-free, obviously, it's a low water uptake material and has got the property to keep the CTI stable at high temperature. And when I said high temperature, I mean 180 degrees C max. Finally, right-hand PPS is virtually resistant to every kind of chemicals, so it's answer to the CTQs when it comes to the AC roads in terms of chemical aggressions. What do we expect on a material standpoint of view for the housing? We need a material which is first flame retardant V0. We need a material which is high heat resistant. We need a low water uptake. We need allergen free to avoid any risk of corrosion. And finally, we need a material which blocks all the electromagnetic interferences, what we call the EMI.
EMI is any electromagnetic signal that can interfere with the proper operation of your electric vehicle. Just like you can use the magnetic field that's generated by the magnet wire to power your rotor in your e-motor, unwanted or stray signals can also interfere with your inverter system. The housing needs to protect the components inside from noise generated by other components inside the same car, from components in other cars, or even from noise generated by something like your phone. Some standards define the upper limit of acceptable noise outside of the housing, but we can also measure the shielding effectiveness of a material or how much noise it blocks.
Until now, all the inverters you can find on the market are produced in aluminum. However, we think that to produce them in polymer could be a good idea because with polymer we can integrate flame retardancy, allergen-free, we can damp the vibration and reduce the NVH, and we can integrate EMI shielding efficiency inside the material. Talking about weight saving, here one example. This is an aluminum lid for an inverter. As you can see on the scale, roughly 800 grams. Let's talk about the same part made with polymers. These parts combine all the benefits from retardancy, EMI shielding, NVH amortization, plus weight saving. Have a look. A bit more than 400 grams. So here, what we offer, it's basically, in terms of weight saving, a discount of 40–45%.
We hope you found this video interesting and informative. If you have any additional questions about our solutions for power electronics, please don't hesitate to contact us.
And now you know how we enable cleaner, safer,
and more energy-efficient mobility.